Kia ora tātou. So far we've looked at the single source shortest paths problem, which is finding the shortest path from a given source node to all other nodes in the digraph. An obvious extension of this is to look at multiple sources and ask, what is the shortest path between any pair of nodes? This is called the all pairs shortest paths problem, or APSP problem, and in today's lecture we'll look at an algorithm called Floyd's algorithm that efficiently solves it. So first, notice that a solution to the all pairs shortest path problem can be presented as a distance matrix. So for a digraph which looks like this, we'll have a cost matrix that looks like this, where we've used infinity to indicate the absence of an arc. So there's no arc from 0 to 0, there's no arc from 0 to 2. And that has a solution which is this distance matrix, which shows that the cost of the shortest path from 0 to 0 has length 0. The cost of the shortest path from 0 to 1 is of cost 2. The cost of the shortest path from 0 to 3 is 3 via this route. And for example, the cost of the shortest path from 2 to 3 will also be 3 up here and down here. So clearly, if we have a method for solving the single source shortest path problem, which is essentially solving the all pairs shortest path problem for a single row of the distance matrix, we can solve the all pairs problem by running the single source solution from each node. For example, we could run Bellman-Ford from node 0, then node 1, then node 2, then node 3, and fill out this matrix. Multiple applications of a single source solution can be sensible where conditions are right. We can apply Dijkstra multiple times at a cost of big theta n times m log n if we're using an efficient implementation. Recall that Dijkstra is only valid when there are no negative weight edges in the digraph. And when m is large, so when the graph is dense, this starts to get unwieldy. Looks more like n cubed or more. Using Bellman-Ford, the cost would be big theta of n times m. So typically somewhere between big theta n cubed and n to the power of 4, depending on the sparsity of the digraph. The obvious advantage of Bellman-Ford over Dijkstra is, of course, that it's robust to negative weights. There is, however, another solution to the all pairs shortest paths problem known as Floyd's algorithm that is also robust to negative weights and has a running time of big theta n cubed regardless of the density of the digraph. So it's faster than repeated applications of Bellman-Ford, certainly on dense digraphs. The basic idea of Floyd's algorithm is to find the shortest paths between nodes using only a fixed set of intermediate nodes. This set of intermediate nodes grows from the empty set, so we'll initially consider only nodes that are neighbours, and then it grows one node at a time until it includes all nodes and the algorithm is complete. As well as being reliably cubic in its runtime, it is a simple structure of 3 nested for loops, which makes it easy to program. So let's have a look at the pseudocode. So Floyd simply takes as the input the weighted digraph with weight matrix C. We start by initializing the distance matrix D, setting as first pass to the value of the cost matrix. Then we get to the main loop, where this outer for loop steps through each node, essentially adding it to the set of intermediate nodes, and then the inner 2 for loops cycle through all pairs of nodes u and v, seeing if a shorter path between u and v can be found by using the most recently added intermediate node. So we see whether we can update the distance matrix D at uv by considering the distance from u to x plus the distance from x to v. Now you can see exactly why this is a cubic algorithm and it's costly to run by hand. But we'll have a look at a small example to get an idea of how it works. Here is the weighted digraph we saw earlier, and I've initialized the distance matrix D to be the cost matrix, and you'll notice that to work here we need to start with zeros down the diagonal of the cost matrix. So as usual, we can process the nodes in any order, and we'll just go in the order 0, 1, 2, 3, 4. So initially I set x to be 0. And I'll be asking if for any pair of vertices u and v, we can get a better distance by using the path from u to 0 and then from 0 to v. When I look at this number here, this represents u and v are both node 0. So is 0 greater than the sum of 0 plus 0? No, it's not, so we'll leave it. Is 2 greater than the sum of 2 plus 0? No, it's not. Is infinity greater than the sum of infinity plus 0? No, it's not. Is 4 greater than the sum of 4 plus 0? No, it's not. So we change nothing in that first row. How about this infinity here? So now u is 1 and v is 0. So I'm going to say, is this infinity greater than infinity plus 0? No, it's not. How about is 0 greater than 2 plus infinity? No, it's not. Is minus 1 greater than the sum of these two infinities? No, it's not. Is 1 greater than 4 plus infinity? No, it's not. We're on the second row now, corresponding to node 2. If we look at 1, is that greater than 1 plus 0? No, it's not. Is 2 greater than 2 plus 1? No, it's not. Is 0 greater than 1 plus infinity? No, it's not. Is infinity greater than 1 plus 4? Yes, it is. 1 plus 4 is 5. So we're going to replace this infinity, representing the distance from 2 to 3, with a 5. And we'll leave that in blue just for now until we get to the end of the iteration to show what changed during that iteration. How about this infinity? Is that greater than infinity plus 0? No, it's not. This one, greater than 2 plus infinity? No, it's not. It's minus 2, greater than infinity plus infinity? No, it's not. Is 0 greater than 4 plus infinity? No, it's not. So we've completed the first iteration of this outer for loop, and this is our current distance matrix. So I've just changed the color of that number, and now we'll update x to be node 1. And again, we go through this matrix at each point, comparing two numbers and seeing if it's an improvement over the current number we're looking at. So is 0 greater than the sum of those two numbers? No, it's not. Is 2 greater than the sum of these two numbers? No, it's not. Is infinity greater than the sum of these two numbers? So 2 minus 1 is 1, so we can update this infinity to be 1. And is 4 greater than the sum of 2 and 1? Yes, it is, so we can update this distance as well. Now, is this number greater than the sum of those two numbers? No. We can leave that alone. We can leave that alone, and we can leave this alone. How about this number here? Is that greater than the sum of those two numbers? No, it's not. Is this 2 greater than the sum of 0 plus 2? No, it's not. Is this greater than the sum of minus 1 and 2? No, it's not. Is 5 greater than the sum of 1 and 2? Yes, it is. So we can update the 5 to be 3. Let's look at the last row is this infinity greater than the sum of these two numbers? No, it's not. Is this greater than the sum of these two numbers? Is this greater than the sum of these two numbers? No, it's not. Is this greater than the sum of these two numbers? No, it's not. So we've again completed an iteration of the outer for loop. We can update x to take the value 2. So let's just go through one more iteration and then you can do the last one yourselves. So we'll be looking at this number and comparing it to the sum of whatever's in row 2 and column 2. So is 0 greater than 1 plus 1? No, it's not. Is 2 greater than 2 plus 1? No, it's not. Is 1 greater than 1 plus 0? No, it's not. Is 3 greater than 3 plus 1? No, it's not. On to the row corresponding to node 1. Is infinity greater than 1 plus minus 1, which is 0? Yes, it is. So we'll update this infinity here. Moving on, is 0 greater than 2 minus 1? No, it's not. Is minus 1 greater than minus 1 plus 0? No, it's not. Is 1 greater than 3 minus 1? No, it's not. Is 1 greater than 1 plus 0? No, it's not. 2 greater than 2 plus 0? No, it's not. Is 0 greater than 0 plus 0? No, it's not. Is 3 greater than 0 plus 3? No, it's not. So we can move on to this last line. This infinity, is that greater than 1 plus minus 2? Yes, it is, because that 1 plus minus 2 is minus 1, so we can replace this. Similarly, infinity is greater than 2 minus 2, which is 0, so we can replace this distance of infinity with the distance of 0. Now we'll finish off this iteration. Is minus 2 greater than minus 2 plus 0? No, it's not. Is 0 greater than 3 minus 2, which is 1? No, it's not. So we've finished this iteration. Let's change the color of these numbers. We'll increment x up to 3, and we can run through the same thing again. And I think you'll find, if you do that yourself, that there are no changes at this last iteration. So if you've checked this for x equals 3, you'll see that there's no further changes at this last iteration, and we'll return this distance matrix. And in fact, I should have had in the pseudocode that we return D. So we've seen how Floyd's algorithm works, and it's obviously very simple to code up. Let's now look at how we can prove that Floyd's algorithm is correct. Our approach will again be an induction approach on the number of times we've passed through the outer for loop. Each time through the outer for loop, we're adding a potential intermediate node x. We'll show that when we're at the bottom of this loop, D records the shortest length paths for all pairs where the paths only use the intermediate nodes seen to date. Since we go through the outer loop n times and see every possible intermediate node, by the time we're at the end of the algorithm, the matrix D corresponds to the distance matrix for the digraph, and we've solved the all pairs shortest paths problem. So let's formalize that. So the statement we prove is this one. At the bottom of the outer for loop, for every u and v in our node set, then what we record in duv is the length of the shortest path from u to v using only intermediate nodes that have been seen in this outer for loop. And we'll prove this by induction on the number of times through the outer for loop. First, we'll need to define a few things. We'll let Sk be the set of nodes that we've seen after k times through the outer loop. And we'll define a SK path to be one whose intermediate nodes belong only in SK. So if we've got a path from U to V, anything that is not U and V belongs to SK to be an SK path. And we'll say that the lowest weight SK path has cost dk. So what we need to show is that for all k, after k times through the outer for loop, dk of uv is the minimum length of a sk path from u to v. So we'll show that after k times through the loop, dk uv is the minimum length sk path from u to v for any nodes u and v. So the base case of our induction proof is when k equals 0. In this case, we haven't been through the for loop at all, so S0 is just the empty set, and the result holds. And the result holds since any path is just a single arc, and before we run through this for loop, we've set D0 to be C. So now we'll assume the result is true after k times through the outer for loop, and we'll consider what happens at the end of the k plus first time through the outer for loop. So let's suppose that x was the node added on the k plus 1th pass through the loop. So we have that sk plus 1 is just the union of sk and the single node x. So we'll consider two nodes u and v that we've chosen here, and they could be anything. And we'll let L be the minimum length of an sk plus 1 path from U to V. Now we have the following inequality. L is less than or equal to dk plus 1 of UV. How do we know that? Well, L is the minimum length of an sk plus 1 path, whereas dk plus 1 is either infinite or the length of some sk plus 1 path, so must be at least as large as L. So we need to show the reverse inequality, and that'll give us the equality. So we need to show that dk plus 1 of uv is less than or equal to L. Well, how do we do that? We'll choose an sk plus 1 path, and we'll call it gamma, that goes from u to v of length L, and we'll consider two cases. So gamma is an sk plus 1 path of length L from U to V, and the two cases we'll consider are when x is not on gamma and when x is on gamma. So the first case is when x is not on gamma. Well, if x is not on gamma, gamma is simply an sk path, so the result holds by the induction hypothesis. So if x is on the path gamma, then we're going to split the path gamma into two subpaths, gamma 1 and gamma 2, where gamma 1 goes from u to x and gamma 2 goes from x to v. Then gamma 1 and gamma 2 are both sk paths, that is the intermediate nodes of gamma 1 and gamma 2 all lie in sk. So again, we can use the inductive hypothesis to get the following. So we have the cost of gamma, which is L, is the cost of gamma 1 plus the cost of gamma 2, because gamma 1 and gamma 2 just came by splitting gamma at x. And by the inductive hypothesis, since they're both sk paths, then we have that the cost of gamma 1 is equal to dk ux. The cost of gamma 2 is equal to dk xv. And we have from the update formula that this sum must be at least as large as dk plus 1 of uv. So you have that L is greater than or equal to dk plus 1 uv. L is less than or equal to dk plus 1 from u to v. So equality holds. L is equal to dk plus 1 uv, and the result holds. In the proof we just saw, there was no assumption about arc weights being positive, so Floyd's algorithm will work with negative arc weights. But the problem makes no sense when there are negative cycles. So how can we find these? Well, recall that the Bellman-Ford algorithm could detect negative cycles by running the algorithm a second time, starting at the completed dist array. Floyd's algorithm is a little simpler. All we need to do to see if there are any negative cycles is to check the values on the diagonal of the returned distance matrix D. If there are no negative weight cycles, the lowest cost path of any node to itself, DUU, is just 0. But a node that lies on a negative weight cycle will have DUU less than 0. So any negative values on the diagonal of the matrix D indicate the presence of a negative weight cycle. So we've come to the end of this section where we've looked at finding the minimum cost paths in weighted and unweighted digraphs. We've considered a number of algorithms for doing so. BFS, which works on unweighted digraphs, Dijkstra, Bellman-Ford, and Floyd's algorithms. As an exercise, I'd encourage you to make a table like this that displays the running times of each of these algorithms for solving the single source shortest paths problem and the all pairs shortest paths problem, and to consider which algorithms are robust to the presence of negative cycles. So in here, we would put the running time for BFS on the single source shortest paths problem, and of course there would be an asterisk next to that because BFS only works on unweighted digraphs, whereas these three all work on weighted digraphs. So I'll leave it to you as an exercise.